Welcome back to our Sets in Scala programming language lecture, second part, and we will look at some operations from set theory in mathematics, right? So we'll talk about things like difference, intersection, union, right? So those things which are in the math. But again, I think it's quite reasonable, right? Nothing to be scared of. So let's see how it looks in our programming language. So what does it mean? So again, we have some sets of, in this case, unique values, and we want to do some operations. I think it's easier to do this when you do actually some, see it in practice. So let's create some sets again. We already have some sets, but let's create some more. 1 to 5, for example, will be, and I'll do 1 to 5, of course, and I'll convert it to set, right? Easy. And I'll do another one, maybe, and 3 to 7. Again, it will be 1 to set, right? Not 1, but of course I should type what I write as a variable name, right? To set, right? And we can print these ones, right? And print line, right? And 1, 2, right? And print line. So it should not be any surprise that this will print those sets, right? And we of course the previous code as well, right? And we remember this code while it's running, right? It should be soon available, right? Notice again, of course, that this hash sets, the last entries, again, order is not guaranteed, right? Again, where is our code repository? Of course, it is here at GitHub, RCS Scala Playground March 22, right? Again, and of course in our Scala subdirectory. Okay, so let's do the intersection. So what's the idea behind intersection? With intersection, we want all elements that are common in both sets, right? So that's the core idea. In mathematical terms, it will be this operation, right? This will be the intersection. Again, we don't use this in programming, right? But this, if you took it math in school, that's the actual mathematical symbol. So we are going to combine, right? So of course it will be something like this. And 3 to 5, right? Of course, will be what? And 1 to 5 intersect, right? In fact, that's here, intersect, and it expects. Again, we can use parentheses here, by the way, right? We could, but this is a short way. We could do n3 to 7, right? Intersect, and also n3 to 5 as well. Also will be, we can use this. I like this personally. I'm more used to this language because, of course, I come from Python world, right? And some other language, and this is where it's used as well. Very common. So same as above. Same as above. Notice single, not double, or single, right? Not double, right? So, and of course we can print them, right? And of course, again, I'm writing the names. We should expect those values there. A question, will they be there, right? Again, it makes sense that they should be there also, right? But since we are intersecting, right, we have values 1 through 5, right? And we have values 3 to 7. So only which values are common? 3, 4, 5 are the common values, right? So I hope you agree with me there that those are the values. In fact, that's what they are. Again, if you want them ordered, right, you can have a sorted set, or you could use them to array or sequence of any type and sort it there. All right. So that is intersection. Quite again, not I think quite intuitive concept. That's why set theory took math world by storm in the late 19th century, right? And again, so what's useful? Again, we have these two huge data sets. Again, I mean, we could write some loops and do it by hand, but that would be completely pointless and unproductive, because we have these nice set operations which will do it much faster than we can write the code, right? We have these two collections, and we want to basically get only the ones which are items which are common to only these two, right? Again, we'll see in database and some other technologies it's also used, this concept. Okay, so let's move on to second major category. If this makes sense, we can also perform a union. which means we get all unique values across both sets, right? So similar, we only have our n 3 to 5, we have 3 to 7, so what we'll have 1 to 7, right? Again, 1 to 7, we will do n, right? Because I can't start with like this. That's not a variable value, right? So 1 to 7, right? Again, maybe not the best names in practice, but in here for teaching purpose, good enough name for as a value, right? So again, we had intersections, so it will be what you think, 1 to 5 union and 3 to 7, right? And again, we expect we'll have 1 to 7 there, right? So similarly, how we saw it here, we have another way of writing here. So n1 to 7 also, right? And it will be n1 to 5. And what do you think? It will be, and I'll make it so I'll do it since I demonstrate that it's of course works from both sides. Idempotent, I guess is the word, right? And we can use a single, right? We can single, notice single, right? n1 to 5, right? Again, notice same as above, notice the single, right? Instead of in or, right? In logical or, right? So single one, but again, the idea is very similar. So what we're looking at is this operation, right? Union of all possible values, right? Okay, let's print these out. Let's print these babies out, and we can see what's happening. 7 also. Let's see if they work as we expect. Maybe there's a typo, maybe there's a logical error, but looks like they work exactly as expected. Right, in fact, let me go crazier. We can do something. Well, we have some sets already. What do we have, right? Multiple union. We can do this, right? We can do n3 to 7. We can do n, maybe, what else? What other sets we have? We have a bunch of sets. Of course, these are integers, so maybe set array. We can do array, but maybe something bigger. Maybe like set with multiple additions. We can do that, of course. Set with multiple additions, for example, right? And we can do maybe set n 1 to 5, right? We can do that. We can unionize. We can union across multiple sets. Same also, of course, we can do also the intersection also across multiple sets also, right? Also intersect as well. So let's see what happened here. Print line, multiple union. Let's check if this is again. So let's print it. Indeed it is. It worked fine, right? We have those numbers, right? So we joined all three. Again, I say join, right? Because I'm talking about database terms, but yes, this was a union across 3 sets, right? We could probably look up a picture somewhere across, right? And so on and so on. We can, oh, sorry, excuse me, I'm going to commit it pretty soon. So we can also use intersection across multiple sets. Okay, incidentally. So what else do we have? We have union and intersection so far. We can do something called the unsymmetrical difference. In fact, we use this. I believe we used this here. We used it earlier. I believe this is what we used here. In fact, somewhere here. Remember? Yes, this I think is the same thing. It's a difference, right? I believe it is a unsymmetrical difference. So what is this unsymmetrical difference or regular difference? Difference, right? Not symmetrical. Yeah. So what does it mean? It's this part here written in data set theory terms. We take from the left side all values that are unique to the left side. On the right side, all those are discarded. So how do we write this? Let's do this. So values n1, again, they are not symmetrical. So by necessarily, so we have 9 to 5, right? and again I'm already the value of this name is already giving the game away, so to say, right? Because 3 to 7, right, those values will not be present. 1 and 2 are unique to this particular set, so obviously, well, they will be preserved, right? So similarly, right, it will be val n6 to 7. And can I use this other thing? Can I do this? Let's try. I'm not sure if I can, but maybe we can. Can I do this? Yes, we can. And let's see if it is indeed the same. Well, obviously not the same result, but the same operation, right? Print line 9, 6 to 7, right? So here again, not symmetrical, same operation as above, but not the same result, right? Not symmetrical, right? So that's, of course, keep in mind, right? Everything is clumped twice just to make the point. So let's see if this is really the case. Yes, 1, 2, 1, 2. In fact, it says that the book, well, let's check, or documentation. Where is my documentation on sets? Somewhere here, right? It says actually this should be the actually, right? Minus, right? It's kind of interesting. Except, well, removal, right? I personally like this language, this better than this. Who remembers that, right? Then you might as well use diff. So there's theoretically, you might want to explore, theoretically there might be some difference, but I don't see the difference here actually of operations, right? Except the element of ys, right? All elements of x except elements of ys, it's same, it's by definition, that's a difference. That is a difference here, right? Okay, but these might be maybe slightly faster, right? And mutables, we saw all of those already. Cloning, we saw that. Update, we saw most of these. So what else do we have left? We have do we have a symmetrical difference actually? And I believe we don't actually. Is there well, there is an operation, right? Do we have a operation meaning values unique to this and this? But I believe it's not, does not exist here, right? So okay, so there is also so how to, if symmetrical difference does not exist in Scala collection, we can make it really easily ourselves. How? We simply union of these, right? So sim val sim diff will be what? In this case, right, n1 to 2, and of course union, right, 6 to 7, right? So we made our own hand coded, right? Right, so that should be, of course, print line sim diff, right? So of course ourselves we create the union of both differences, right? We took earlier, right? So that would be a symmetrical difference. Again, I don't see it in documentation. Maybe it exists somewhere. If you find it, you can let me know. And let's see if it runs. No, it should be, of course, 1, 2, and 6, and 7, right? Yeah, indeed it does. Okay, so that's symmetrical difference. That would be this case here, right? Okay. Do we have? Of course, we don't have a negation, right? We can check if things exist. So let's see. We can check if items are strong, are a subset, if set is a subset of another set. Let's check, right? So let's do this. Print line. I will do this n1 to 2, right, is subset of n1 to 7, maybe. Yeah, we do have that, right? Or maybe, right, is it? Yeah, it's here somewhere. An answer will be, of course, this n1 to 2 subset of, did I write correctly? I didn't write correctly. Subset of, right, of another set, right? We have a method here, and we'll call it n1 to 7, right? And we need, of course, a quote, right? And let's check what the answer is. Do we have a quote missing? All right, we have a quote missing here. We have a curly brace missing. Not that. That's not curly brace. That's curly brace there. Okay, so that should be true, right? And similar, of course, it should give you also answers for negative if you don't have, right? And we can check. Maybe let's see, 3 to 6 is answer of subset of 6 to 7, right? Of 6 to 7, of course, it should not be the answer, right? Yeah, it should be obvious, right? Yeah, false, right? And this is true. Okay, so basically checking for is this belong inside, right? Is it inside or not? Okay, so well, where else can it be interesting? We can do, of course, things like this. By the way, we can check again. We can check uniques. For example, uniques, unique characters, unique car set is, let's say again, abracadabra, for example, abracadabra, right, to set. So simple, right? And we have to set, and of course this will be what? A set of characters. Well, naturally, right? So we can print it out, right? And we can also, of course, do things with that. That's kind of nice, right? So we can simply get a pass, a sequence, useful, nice, useful to get unique characters, right? Quite nice, right? So that would give us a set of characters. And of course, we could also do split. We can check for unique words, right? We can pass any type of sequence here and check it set and check for words as well. So let's see if this works. Yeah, A, B, C, R, D, right? Those are the unique letters. So how about words? Well, let's do that. So let's do something like val words, right? We'll do my C spot run, right? Run spot run. Of course, these are, so we have, what do we have? If you're gonna split by spot, of course, is the only one which is duplicate. Everything else is unique because we are not getting rid of all these punctuation marks, right? So let's split, right? So sentence, this will be a sentence, obviously, not the words. This is sentence, right? Let's name our variables. So of course words will be sentence split, right? We already know this technology, this idea. We'll use the regex of space, right? We can use, of course, as a regex, and so we have words, right? And we can create a set, right? So let's check unique words, right? Unique words will be words to set, right? And we can print words, and we can print unique words. And we'll see the difference, right? Print words, this will need probably, is this an array? No, it's an array, so we need to make a string, and I'll do maybe space. Again, we go back, deconstruction and construction, right? So in effect, well, we deconstruct in effect reconstructing the original text, right here, right? But that's not part of our lesson here, right? But we also want to print the unique words, right? So unique words. So again, so you don't have to. So these unique words is a set of strings, right? Makes sense, right? Because we have an array of strings. So when we convert an array of strings to a set, it will be a set of strings, right? Again, these strong types, again, helps us avoid any typing mistakes, right? Because it will pick up immediately if you make a mistake. Again, I still have some warnings. Let's check. Let's run this whole thing. Maybe there's some depreciated instructions. Yeah, so C spot run, run spot run. That's our array, right? So how about hash set? Run spot run. Again, we have these extra commas, right? Of course, right? Again, so we have run with exclam, right? That's one unique. How about spot? There's only a single spot because spot on spot, right? So that was actually unique here. Of course, we could have replaced. Sorry, we're gonna end this. So we'll see about some exercises after the in the next lecture, right? We'll see some exercises to utilize this. So to do some exercises to practice our newfound set operation skills, right? We'll do some set